All right, this is a problem done by request from someone in the comments. Feel free to request problems to be done. It is an AIME problem. I am not focused on the AIME right now as far as content goes. I want to pump out every single AMC 10 question from the year 2000 on. That is my main priority because it gets more views and it's what the viewers want. This is more niche content, but I will do it anyway because it's fun to do. So I will do these periodically, but I'm not always going to be focused on the AIME. All right, so the 2011 AIME number 1, problem number 10. The probability that a set of 3 distinct vertices chosen at random from among the vertices of a regular n-gon determine an obtuse triangle is 93/125. Pause and make sense of what you read. N-gon is just a polygon with n sides. Regular, all angles and sides are equal, right? And we want 3 distinct vertices of that regular n-gon. 3 points make a triangle, and we want to know that the probability that that triangle is obtuse is this value. So how can we approach? Find the sum of all possible values of n. It seems to imply there's more than one value of n. It could be there's only one, but it seems to imply there's more than one. So there are false approaches. You have 3 hours on this test. That's an average of 12 minutes per question. There's 15 questions, and so you spend less time on the earlier questions, more time on the middle and later questions. This is problem number 10, the last problem of the middle 5, and usually it's kind of a gateway problem to getting qualified for the USAMO or USAJMO, as getting 10 right, assuming you got the first 9 correct, is a good amount to aim for if you did decently on the AMC 10 or 12, whichever one you took. So having said that, don't be rushed for time. Just think, what's the best approach? And if you take a false approach in a problem, especially on the AIME, don't freak out. Abandon that path. For instance, when I first started this problem, I thought maybe we should focus on the denominator of 125. If we do that, you know that the total number of points, n, choose 3 of them, because n being the n-gon, needs to equal some multiple of 125. And I played around with this, I tried doing synthetic a little bit. It was a total waste of time. It doesn't produce any fruit, and there's so many possible values for x, you don't want to be doing it all day. And it takes a long time. So it's just not a good use of time. And when that happens, when you recognize that's happening in a problem, feel free to abandon that path and go back to the beginning and pick up a new one. I'm not going to show the abandoned path for the sake of the video. We will go to a different approach. What about n? Well, n is an integer. Okay, if we can't think about, somebody's going to have probably some big values of n to get that kind of probability. What would happen if we had small values of n? Let's just explore a little bit. Let's say there's 6 sides, right? A hexagon. Let's make a picture of a hexagon. And the thing about regular n-gons, you kind of want to mine, M-I-N-E, mine your mind for key facts and concepts. And there's a concept you should be thinking of, and that's that all regular n-gons can be inscribed in a circle. So if I inscribe this in a circle, why would I want to do that? Well, because it might help us think about this obtuse concept. Why? Because in circles, any triangle inscribed in a semicircle is always a right triangle. So if we go here to here, for instance, with 2 of the endpoints being on the diameter, that will be a right angle every time. Most of you probably already knew that. The reason is that this is an inscribed angle, and an inscribed angle is always half the arc it intercepts. You can review such concepts in volume 1 if you need a crash course on it. So this would be 180 since that's a diameter, and half of 180 is 90 every time, no matter where the third point is, as long as 2 of the points are on a diameter. Okay, well, what does that mean about obtuse then? Well, to be obtuse, I need to open that right angle up. So I need to pull this point back a little bit, which means I want on my circle, if this is the endpoints of a diameter, I don't want this point, I want a point like here and another point here, for instance. Because this arc now is more than 180. And since it's more than 180, the inscribed angle it creates is necessarily going to be obtuse. So then the goal is, how can we think about that in terms of the inscribed polygon of that circle? Well, we should think about a diameter. We need to introduce a few concepts, and the thing about these concepts is this is not something you learn in a class. I mean, you can kind of, but a lot of times you have to invent the tools that you're going to use on a problem. And so we need to kind of invent some way of thinking about these 3 points in order to classify them. So if we have 6 sides, we notice that's an even number. If I take a point, let's label these vertices, V1, V2, V3, V4, V5, and V6. If I wanted to make a diameter using the vertices, right, then those vertices, if I chose V4 as 1, the opposite end of the diameter is V1, such that this is the diameter here. Okay, but what happens if this number of sides is not an even number? Like what if I have a pentagon, right, something like this, then I'm not going to draw the circle to save time. I could draw the diameter from one vertex would not pass through another vertex. Instead, it would pass through the midpoint of an opposite side to hit the circle over there, right, just outside the regular pentagon. Okay, so this had 5 sides, and it doesn't pass through vertices. That kind of tells us we should probably be thinking about 2 different problems. One with an even number of sides and points, vertices, and one with an odd number of sides. So then we want to think about other related concepts. How do we represent an even integer typically? Even integers are usually written as 2n or 2x, but n is commonly used. Note that this n is not the same as the n-gon n. Just forget about the fact that they look the same. We're just going to use n though because it's kind of standard for even integers or whatnot. So odd integers is 2n plus 1 or 2n minus 1. These are the most commonly used. Technically, you could make it plus 3 or plus 5 or minus 3 or minus 5. All of those are okay to make odd integers as well, but these are most commonly used. So I'm going to use this for evens, of course, and I'm going to use 2n plus 1 for odd. And we break it down into 2 cases. If 6 sides exist, then 2n will equal 6 and n will equal 3. We want to introduce a concept we're going to call the leftmost point. And it's important you understand what we mean by leftmost point. What if I had chosen, because leftmost point would be the first point we choose of the 3 points that we're choosing, right? 3 distinct vertices. Let's say that I chose V2 as my first point. How can it be the leftmost point when it's on the right of the picture? Don't think that way. We need to think of it as if I start at this point and go counterclockwise around the circle, imagine you're sitting in a seat at V2. The people to your right would be V1, V6, V5, and so on. And these would be people to your left. So starting from V2 and going counterclockwise, V2 being the leftmost point, it's not really left from the board, but from the perspective of V2 sitting in a seat looking at the circle. Even though there's no people and there's no table and no chairs, we can still think of it that way. It's similar in concept. So the points to the right of V2 are V1 and V6. I can't choose V5 in a hexagon because it won't make an obtuse triangle. Because then I would have V2 and V5, which are opposite points of a diameter, and therefore would create a 90-degree angle no matter which other point I used. So we don't want to do that. So if I consider V2 the leftmost point going counterclockwise around, my other 2 points to choose from are V1 and V6. Similarly for V4, my 2 points I can choose from are V3 and V2. And sure enough, this angle is going to be, if I made this the triangle right here, V4, V3, V2, that would be obtuse. In fact, that's the only obtuse triangle you can make with the hexagon, with V4 being the leftmost point. But we want to think about how can we turn this into probability, right? We need to use combinations, so we're going to say choose for combinations. First, my first choice that I make is which is the leftmost point. I'm going to have 2n choices for that. For this case, the case of having an even number of sides. And then the second choice is what other 2 points do I use? Since this is my leftmost point, or this is, the 2 points to the right of it are the ones I get to choose from. But we know there's 2 choices here because there's 6 sides, but what if there's 8 sides or 10 sides? We're going to think of it in terms of n. So there's 2 points here, and n is 3. maybe the 2 points I have to choose from are just n minus 1, choose 2. Maybe. Let's look at an octagon. And that's the thing. We are introducing concepts, exploring it, looking for verification that our conceptualization of the idea is accurate, right? So we want to check it just to make sure. We don't want to do a whole bunch of work and then find out that was not the proper approach. So if I make an octagon, right, something like a stop sign, you may be better at drawing than me. I'm not the best artist in the world. Does the same thing happen? Are opposite vertices a diameter, basically, here and here? Yes, that's a diameter of a circle inscribed in a regular, or a regular octagon inscribed in a circle. So how many points can I choose? Again, I cannot choose these points. If I call this V1, V2, 3, 4, I'm not going to write it, 6, 7, 8, just save time. This would be V6. I can only choose V5, V4, and V3. So how many other points could I choose from after the choice of V6 as my leftmost point? Well, again, this would be 2n equals 8 and n equals 4. And the other points to choose, meaning this selection, I had 3 choices to choose from. You'll notice that 3 is 1 less than 4. This is a valid approach to count the ways I can choose 3 vertices, right? That will create an obtuse triangle. Okay, then how many total choices do I have? Well, the total number of choices is the total number of points, which is still 2n. Choose 3. I could choose any 3 points, right? And that will be 2n choose 3. So this must be the probability that I get 3 points that make an obtuse triangle, because this is the number of ways, right, to get an obtuse triangle. It's basically fundamental counting principle, the number of ways to choose the first point, which we're calling the leftmost point, times the number of ways to choose the other 2 points, over the total number of ways to choose 3 points from an n-gon that has an even number of sides. We would need this to be equal to 93 over 125. Okay, let's go from there. I'm going to erase this to make some board space. So we'll leave the 5-sided one up for our other thought later. So we're going to have, let's do the algebra now, 2n times, this is n minus 1 choose 2. You should know how to set up combinations. That will be n minus 1 factorial over n minus 1 minus 2, which is n minus 3 factorial, and then 2 factorial. This will become 2n times n minus 1 times n minus 2 times n minus 3 factorial over n minus 3 factorial times 2. 2 factorial being just 2. And the n minus 3 factorials cancel. In fact, there's a shortcut for things choose 2. If you have n choose 2, for instance, it's n times n minus 1 over 2. It's worth remembering that shortcut. How could we have applied that shortcut to this? Well, instead of it being n, it's n minus 1. And instead of it being n minus 1, it's n minus 1 minus 1, which is n minus 2 over 2. And that's what we got. So we could have used the shortcut, and you should have used it if you were doing this problem on the test. Now, this 2 can cancel this 2. And now I will have n times n minus 1 times n minus 2 over this. And this is going to be 2n factorial over 2n minus 3 factorial, this minus this, times 3 factorial, which is just 6. Okay, so this is the big fraction line. We're going to take this and flip it and multiply. So that's going to give us n times n minus 1 times n minus 2 times 6 times, I don't know, times 2n minus 3 factorial over 2n factorial. Okay, so now how is that going to work? Okay, so this is going to be reducing. It's going to become 2n times 2n minus 1 times 2n minus 2 times 2n minus 3 factorial, which is just going to cancel. Okay, so then now how does that write? We now have n times n minus 1 times n minus 2 times 6 over 2n times 2n minus 1 times 2n minus 2. So the n's cancel here. The 2 goes into the 6 3 times. And 2n minus 2 is really 2 times n minus 1. So this will cancel here to give another 2. And I will have 3 times n minus 2, which is 3n minus 6, over 2 times 2n minus 1, which is 4n minus 2. This needs to equal 93 over 125. We cross multiply. 375n minus 650 is 750 equals, oh, yeah, I guess that's true. Okay, equals 93 times 4, 360 and 12 is 372. And 93 times negative 2 is negative 186. So there's an n here too. So minus 186. We're going to move 372n over here to get 3n. And we're going to add 750 over here. So 750 minus 186. What would be 75 minus 180? Or 75 minus 18 would be 657, right? So it would be 570 if I did 750 minus 180. And then take away 6 more to get 564. And this is divisible by 3, which is good because 5 plus 6 plus 4 is a multiple of 3. So we're going to divide by 3. 540 would be 180. 3 times 180 is 540. And then there's 24 more, so it's going to be 188. So n equals 188. Be careful, it's not this n. Again, we were dealing with 2n as the number of sides. It's that n in the 2n, and we're looking for all possible values of this n, not the n that we're using. Be careful with that when you use the same variable for different purposes. In fact, we probably should use a different one, but oh well, damage is done. So 2n is 2 times 188. That is 376 sides. So when we have 2n, we get 376 sides. Now we need to do the same thing for odd. Okay, so I'm going to erase all this. Yeah, we don't have board space. We're going to need it. Okay, so when we did the odd situation, again, what if we use the same concept? Kind of once you've introduced the concepts for the evens, we can introduce them for the odds as well, and we're more familiar with them so we can act upon them faster. Again, if I use this as the leftmost point of v1, v2, v3, v4, v5, note that I'm using 2n plus 1 as the total number of points. Then my choice for the values, if this is the leftmost vertex, I can choose the 2 to the right of it to stay on one side of the diameter. Again, if this is 2n plus 1 equals 5, then n will equal 2. For this, not this n, just the n that we're using, okay? So if n is 2, then how many points were to the right of this? There were literally n points. In fact, if I just take away the 1 point that's the left, there's 2n points remaining, and those 2n points have to be split on either side of this point. So have on one side of the diameter, there will only be n points. So then I think this is going to work. Let's try it out. I would have 2n plus 1 choices for the leftmost point, again, from that perspective, going counterclockwise to the right. And then for the other 2 points, I have from the n remaining points to the right of it, without going across the diameter, I would have n choose 2. That I would need to select as well. So the number of ways to choose the leftmost times the number of ways to choose the total number of points, fundamental counting principle, over, again, 2n plus 1 choose 3, the total ways to choose 3 points from this. And this, again, needs to equal the 93 over 125. Okay, so let's make sure this works out. If I had 7 points, for instance, like I don't want to draw a septagon or heptagon, however you want to call it. If I did though, I would have 1 point and then 1, 2, 3 that I could choose from. Notice there would be 1, 2, 3 going this way. So 6 other points besides the 7th point, 3 on one side of the diameter, 3 on the other. And for 2n plus 1 equal to 7, n would equal 3. So these 3 points, assuming this is the leftmost point, these 3 points would be equal to n. So this is valid. This works. Okay? So let's go ahead and calculate. We're almost done now. 2n plus 1 times, using the shortcut, n times n minus 1 over 2. And then it's divided by 2n plus 1 factorial over 2n plus 1 minus 3 is 2n minus 2 factorial times 3 factorial, which is 6. So I'm going to go ahead and simplify this now. This is the one you reduce. The bigger factorial you reduce to cancel the smaller. So just looking at just the denominator of this expression, it's going to be 2n plus 1 times 2n times 2n minus 1 times this, 2n minus 2 factorial, over 2n minus 2 factorial times 6. Now, the 2n minus 2 factorials cancel, and the 2 here will cancel with the 6 to leave 3. Back to up here. My numerator is 2n plus 1 times n minus 1 over 2 times the reciprocal of the denominator. That's going to be the 3 now on top over 2n plus 1 times n times 2n minus 1. Right? And this is going to work out great because this is going to cancel with this. The n cancels here, and you have 3 times n minus 1, or 3n minus 3, over 2 times this. That's 4n minus 2. This is going to be equal to 93 over 125. So now we cross multiply again to get 375n minus 375 equals, we already calculated this, it's 372n and minus 186. So we're going to move the 372n over here to get 3n, and are you serious? Okay, so 375 minus 186 is going to give 14, again 189. And if I divide that by 3, you're going to get n is equal to 63. Now again, that's not this n. When I said, are you serious, I thought that I had made a mistake because I thought it was the same value we got last time. It just looked familiar. So 63 is the n for this expression, for 2n plus 1 being the odd number of sides. So plug 63 in into the n, and you will get 2 times 63 is 126 plus 1 is 127. So we've checked, let's make sure we got it right, the even case, even number of points, and the odd number of points. And we found only one solution for each. There are no other possibilities. There's only even and odd. We can be sure that these two answers, 376 and 127, are the only possible values. So when we add, we get 3 and 1 and 10 and 1. 503 is the sum of all possible values of n. If you guys liked the video, please subscribe. It helps the channel. Hope you have a good one.